All right, so second order half-lives. Because that initial concentration is in the denominator, those half-lives get longer and longer. For a zero order reaction, calculate the general formula for the half-life of zero order. So there's our dependence. There's our time dependence, our integrated rate law. So how do we do that? Get the half-life. We're going to derive the half-life formula. We're looking for T1/2, the time when A at T equals T1/2 equals A0/2, where these are concentrations. The concentration at the half-life is the original over 2, so you have to know that. So let's just plug it in here, right? That's going to get plugged into here. And now the time is, of course, the half-life. So in the zero order case, the initial concentration is in the numerator. And so as that concentration decreases, the half-life is also going to decrease. This also means that if you just have the experimental data, you can plot the concentration versus time and determine which one gives you a straight line. Sometimes it's hard to tell if it's a straight line. So that's one of those things we might talk about today in the lab when we're looking at Excel and how that's going to help us. In this case, we're looking at the zero order, and we've rearranged the integrated rate law to look like the equation of a line. And some of the slopes, some of the lines on here are below the line, like that one's below the line, and that one's kind of on top of the line, but it's a really good fit. They're right on there. Mm-hmm. So in general, we want to make sure that we have a good fit to a line, in that some of the points are above it and some are below, and that they're equally distributed. Rather than, sometimes we'll see one that looks like this. You'll have your line. That may not, they may be really close to the line, but it may be a better fit to a linear or log version. Okay, so we would plot, in this case, we're going to plot concentration versus time. And if it's linear, then we would have a zero order reaction. Or we'll plot log of concentration versus time. And if that one is linear, then we would have a first order reaction with a slope of -k. Let's look at this experimental data. We have concentration and time. That's what we measure. And from it, we can calculate the rate. Of course, we'd always take the initial rate to be a good one. One way we can find out if something is linear would be to look at the slope at the beginning and the slope at the end. So basically those initial rate, that initial rate and the final rate, and see if those are similar. But here you do see this kind of a happy face, right? These are on this side and these are on this side. So that's not the best fit. This is a much better fit over here. Okay, so that's just looking at it visually. For a second order equation, we're going to plot 1 over the concentration. That'll be our y, and then t. It's our x value. And again, here's another set of data, and both of them have that kind of happy face look, right? The points in the middle are on one side of the line, and the points at the extremes are on the other side of the line. So neither of those are that great. This one very well could be linear, right? This one looks like it could be pretty close to the line, but we should check the other. And here you get it's truly linear, right? So this is not a good fit. So you can kind of tell visually And then you can use some mathematical ways to tell. The best way is typically to look at the r squared value, and that should be pretty close to 1. Have you heard of that already when we did like the Beers Law Lab? Did you look at the graphical analysis for that?
Yes.
Yeah, and r squared was supposed to be like 0.9998 or something like that, 0.998 or better, or closer to 1. The r squared value tells us how close they are to the line, and it's taking the distance of every point and minimizing that from our regression analysis. Okay, so if we get a line for the 1 over concentration versus time, then our slope will be k. And that information falls right out of the integrated rate laws. If you have Excel, you can open it up, pop that in, and look at those different plots pretty quickly. Or you could compare the slopes.
Professor, quick question.
Yeah.
So for the zero order and first order reactions, the K is negative, and for the second order, it's positive. Why is that?
That falls directly out of the integrated rate law questions.
Oh, okay. So back in
equations, sorry. I'm trying to get everybody on the page where I can see it. Yeah, so we have, like looking here, you can see that that slope would be positive k. On the earlier ones, the other ones are both negative k. So it's probably useful to make yourself a cheat sheet that has like your order, 0, 1, 2, and then you'll want your integrated rate law equation, and you're going to want your half-life equation, and you probably want your units on k, right? And that would be a good table to construct to use while you're doing problems. So I usually give that to you on exams.
So the difference with the first order and the zero order is that the first order uses like the log of the concentration, but they're both a negative slope.
Yeah, we'll just write these equations in there. So zero order, a at time t equals minus kx minus a naught. Yeah, so in the linear form, bringing it over to the right side, then the initial concentration is positive. And then on the next one, same thing, but it's logs of concentration. And again, I'm not writing it super beautifully because I want you to write your own. It's minus kt plus log of a naught. And then this is going to be 1 over at is positive kt plus 1 over a naught, right? Yes. So go ahead and fill in those. The units on k is helpful just for reference, just to look it up, and your half-life equation, which you know how to derive that, right? You just plug in that t1/2. We just did one of those.
Yeah, there's also a very helpful chart at the end of the textbook on 12.4. It has like the big chart of everything as well.
Thank you. Yeah, and it's always helpful if you copy it over in your own hand and refer to your own. So even if you copy it from the textbook, just that process, you know, it's like using your own hardware. It just gets in there better. So we could compare the slopes here with here. And if the slopes are similar, what would the order be? It would be first order, right? Because that's the one that, oh no, it would be zero order.
No.
So here we have concentration and time. And if we plot concentration versus time and we get a line, then that means it's zero order. Okay, so next up, we're going to check to see if it's first order by plotting the log of the concentration. So let's make a column here where we have log NOBR. So in this case, if the reaction, if the slopes are similar, then this should be which order?
First.
For
First order. And all those time increments are 10 seconds. Yeah, so they all match. All right, so these, they seem like they're not that close. All right, so it's probably not the first order reaction. All right, the next one, we want to find out if it's second order. So if this one is linear, then it would be second order. So I'll make a little column up here, and we're going to plot 1 over concentration versus time. Maybe I'll put it right in the middle. And then that is 1 over molarity. All right, these are much closer. So what we're looking at, we're comparing the slope right here. We're comparing that slope to that slope. If they're linear, that slope is going to equal that slope. So that's what we've done. It's just a quick arithmetic way to do the graphical analysis if you don't have Excel handy. All right, so it looks like this is second order. All right, so now we have to calculate K. How do we get the K?
Can we use the integrated rate laws and the information that we're given in the problem? Can I rearrange one of those equations?
You can use the integrated rate law. What do we have here? Oh, we have just concentration and time data for this.
Right.
Yeah, so that would work fine. So you could use either one. You could say rate equals K times NOBR squared, but you would have to calculate that rate, which you've essentially done, right? Which rate would you plug in here? So that would be one way. Or you could say, I'm going to use 1 over 8. Is that right? Did I pick the right one?
1 over AT equals KT plus 1 over A naught.
Yeah, that one might be a little bit easier because you just plug in those concentrations. We could use the slope from this one, yeah.
Would it be appropriate to average the slopes between a couple of time intervals to determine K, since they're just so slightly different.
You could do that, yeah. Yeah, so there's a lot of different ways to get at that K value. Do we have seconds?
I have it in seconds.
Oh, it's in minutes. I was wrong all along. Those were minutes all along. I know it's getting messy, but hopefully yours are not quite as messy. Okay, here's another problem. So you have a lot of different ways to consider this problem. So go ahead and take some time to work that one out. All right, so what's the first step?
Find some slopes.
Yeah? Remember, in a natural log, those values are very sensitive, so keep extra decimal places. Okay, this one is in seconds.
I'm just setting up a basic y equals mx plus b equation to solve for k.
Yes, once you know the order, then you can use that method with the appropriate y.
Okay.
Or if you've already calculated your slopes, you could take your initial slope and then make it positive or negative depending on what order you picked.
Okay.
They're pretty different though.
That matches what I have.
Yep, got that too.
Thank
Yeah.
you.
Yep.
All right, so which order should we pick?
I said first order.
I agree.
My first order.
Yeah, looks like first order. And
Right.
these are just about 16% different between them.
So if we were really advanced at this, would this be where we would be looking at like something that's like a partial order to get the perfect exact thing?
Not necessarily. When we look at that kind of thing, we're going to be looking at the mechanism. And so we'll have other means to get at that information. So right now we're just doing just a general graphical analysis. And this one is clearly way different. So it's definitely not second order. So we're going to conclude that it is first order. And then from that, we're going to take log of AT is minus KT plus log of A naught. So our slope, so we'll take our initial slope equals minus K. So K equals 0.01215. So what's our rate law?
Concentration of, what was it?
C2H5. I?
Yes.
Yep, and there's our K. We could plug that K in.
What is that compound called? I've never seen
We
iodine.
call it ethyl iodide.
Okay.
I think systematically 1 iota, well, I guess it has to be a 1, so iodoethane. Probably ethyl iodide is more commonly used, but it's not the systematic name. Okay, so we need the half-life. And so that chart becomes handy if you have that tabulated. Or you can always just rederive it, brute force. And is it constant or changing?
Constant.
Yeah, this one's constant. So this is 0.693 over K, right, for first order?
Is that what ln of 2 is? I
Yes.
think so.
Yeah. Yeah, how does that work out? Okay, cool. Integrated rate laws. Here is another one. Now, if you have Excel handy, you can pop it into Excel. You can calculate the natural log of the concentration and the reciprocal of the concentration and check out which one's linear. Or if you're doing it by hand with a calculator, you can compare the slopes of those 2 points again. So once we figure out what trend that follows, then we know the order and we know all that information about what governs 0 first or second order reactions.